When these questions, send an email but include all of us. When they are nice general questions which are not just personal, okay? You help your buddies, okay? Because then I can even send you some notes or whatever beforehand. So I just need to say a few words on what we discussed last day. We'll summarize the CKM, the physics of the quark mixing. The importance, the physics, the structure, and some of the subtleties that we sort of mentioned briefly. So what did we learn last time? That because of non-trivial Yukawa couplings, as Guillermo I think said, I ended up with generally non-trivial mass matrices of quarks, and they had to be diagonalized. And the mass matrix is diagonalized in general by different left and right rotation. If they are Hermitian, as you know, then of course the rotation will be the same. In general, not. So we should assume that it is. And this we could call diagonal Q. And a way diagonal Q, that says diagonal matrix and eigenvalue M1, M2, and so on. And then if there are n generations for Q species. Q stands for that particular quark. Quarks of different charges do not mix, obviously, right? Charges are good symmetry. Mass matrix for up quarks is separate from down quarks, from charge leptons, and so on. Pay attention that I can always choose this to be a real and even positive number. If you put a phase here, I will use the freedom here to rotate the phase of air. Okay, suppose that there was e to the I phi 1, e to the I phi 2. Well, notice that this particular right-handed notation, e to the I phi 1, e to the I phi 2, and so on, is unitary. Therefore, I will multiply it or minus sign and get rid of that. So, well, this you knew. The face of the quark mass field when you write QL bar QR, and here MQ, the phase is not physical. I can get rid of that phase by rotating the. But once I diagonalize it, I can think of a species as if it's just one particular particle, you agree? Once I diagonalize. Okay. They don't mix here anymore. So just reminding you, the phase of the quark field is not physical. You can rotate it away by changing the phase of either left or right, as you wish. We had tacitly always assumed that. Notice if I get off the phase, that also means that the sign is not physical. That you notice immediately, sign can never be physical because E square is P square plus M square. In any case, the only thing that you can measure is M squared by this. By the way we define the mass, this is how we define the mass. We don't put a particle on the scale. We can't do this with this guy. Okay. So when the dust settled, what we learned that the neutral interactions of the photon, Z boson and the Higgs, which we can call neutral current interactions. Well, this is not a current really, okay, which is coupled to side by side, but anyway, neutral interactions, let's call them, are diagonal, no mixing. Diagonal in flavor. Flavor is different species, okay? When I speak of flavor, then I say up quark or jump quark. They are particles of same quantum numbers but different flavor. Down and strange quark would be same particles of different flavor. Ice cream is an ice cream, but it's a different flavor, right? It may be made sort of in the same structure. Well, he has more than a flavor. And then, of course, the W cannot be diagonal Y, because its interaction, we found out, had this form, gamma mu, UL up dagger, ULD, DSB. And this we call VCKM. In the neutron interactions, you will always get U whatever, U, dagger U. But because this guy takes up to down, then it also does with the mixings. So what were the comments? Okay, let's try to summarize the comments which are so important that I made last time. One, it was very important that if the quark maxes are the same, for example, take M up mass matrix. That is to say, imagine that M up is equal M char, equal M top, and so on, equal M0. Then I said there can be no mixing. Remember that?
Yes.
Why? Because take this matrix which has this form, M0 times the identity. That will be a matrix between U, C, T, U, C, T. After diagonalization, apparently, it had this form. But notice, I can rotate this into U, C, T bar, some U dagger, M0, 1, U, C, T, U. Right? All I'm saying, I can rotate UCT into UCT. I'll stop writing dots. I'll pretend that there are 3 generations. Okay? This is invariant because this is unity. So even after the diagonalization, I can keep rotating, okay? Since U dagger U is 1, it's unitary. But then this will go, immediately I will find out that VCKM goes into U dagger VCKM. Because I will rotate here. I won't rotate here. I will rotate here. Right? When I do this rotation, it will appear only here. So you see what I did? We diagonalized it. We were happy. But I said, okay, I'll keep rotating. That's my right. You can always keep rotating it. The only thing, if this was not a unity, okay, this wouldn't be invariant. It would be stupid to do it. You would screw up the mass matrix. You would go back to the original problem, okay. If in general this would be some M here, it would be M1, M2, and so on. Then, of course, you will destroy everything you've done by diagonalizing it, but I keep it diagonal. So in other words, I can now choose U. So now, choose U, U equal to VCKM. Since any U is as good as any other. And lo and behold, the mixing disappeared. So I don't expect mixing when masses are the same. If the masses of some species of particles, either up quarks or down quarks, by the way, you studied neutrino oscillations with Alexei, I can bet. For 2 flavors. Do you remember how the formula for neutrino oscillation goes? It has nothing to do with quarks, okay? That will have to do with Latoni mixing. He talked of neutrino oscillation, saying, well, neutrinos could be massive. Then we have the Cabibbo mixing, or the core, or whatever you want to call it. Do you remember vaguely how that mixing probability looked like? And U equal become nu mu?
Sine square of
There was sine square, bravo, actually 2 theta comes. Theta is the mixing angle, the analog of Cabibbo mixing. Very good.
Sine.
And then sine squared, this is why I called it oscillations. Do you remember what here? This is physics here. Delta M square.
Delta M square over L.
E
Times length
E
or time. The further away you are, the more likely they will have time to oscillate, or distance. Over, it has to be over energy, because the smaller delta, we'll understand in a minute why energy, okay. And maybe there was a factor of 4 or 5. Notice, if delta M square is 0, maybe you didn't pay attention then there are no oscillations. So there is no mixing. There is mixing, you say, but how come? Well, there is no mixing, well, because I can always rotate theta away. I've just argued, just like this with the quartz. Okay? This is a side remark. I'll come back to oscillation. And by the way, this is why the energy has to be there. Because small delta M square is like going to very high energy. So I expect that the bigger the energy, then the less this matters. Okay, so the effect should be small without doing a calculation. I can do the calculation. Okay, side remark. Then we did the phase counting. So this was remark number 1. So in other words, okay, let's remember here. The generate quarks means no mixing. This is very useful information. Then the comment number 2, we counted the phases. And we found out that the number was 1/2 n minus 2. So we needed to go to 3 generation, okay? The celebrated success, the great success of Kobayashi Maskawa, that actually the 3rd generation exists in order to give us CP violation. Why do we need CP violation? You know, these people who like, you know, when the children ask you why, I keep asking, that's a nice question, okay? We live in a strange world that if I touch fork, strangely enough, we don't annihilate each other. He's made of matter. That's very strange, because we would expect a symmetric world.
M minus 1.
Sorry?
M minus 1.
Or n minus 1 maybe.
M minus 1, M minus 2.
N minus 1, N minus 2, thank you. Great. I told you I'm sick today, I will not write. And I don't want to look at my notes. So that means more than 3 generation or equal 4 CP violation. Now it's interesting. It's interesting that this question, why there is CP violation, so okay, just a side remark, you must have heard of that. We live in this strange world in which matter is separated from antimatter. Not only is it separated, it's somehow created, the asymmetry is created somehow, you know, either God-given asymmetry to start with, but this may be the way it is, that the universe started with more baryons than antibaryons. But it would be nicer, people felt, and Sakharov in the 60s, who became much more famous as a Russian dissident than as a physicist, wrote a beautiful paper saying, well, imagine that you live in the world that somehow got to be symmetric, or started to be symmetric, and then you produce the asymmetry through microphysics. In other words, you will need the interactions that violate baryon number, obviously. If there is no difference between baryon and antibaryon, I will have a symmetric world. But also I must break CP, because by CP particle goes to antiparticle, if CP is a good symmetry. So you could say entropically, if you like, entropic principle, we need CP violation so that you and I can be giving a lecture today, and you know. Now that may not be good. So I don't know if it's a good universe. I don't like entropic principle, obviously, but if you like it, okay, you come and conclude. We need CP violation in order to have the so-called genesis, okay. It's a topic worth discussing separately. So 3 generations, and then what else did I say? I think I basically stopped here. The only thing I managed to, I think, to confuse, at least managed to confuse Ahmed, when I was saying we tried to argue, you know, this phase, how physical this phase was, okay? And then I wrote my VCKM. And so there was a rotation on the left. There was a rotation 1, 3 here, I think. We rotated 1, 2 here, and then 2, 3, I think we did, right? So I said, imagine that 1, 2 is 1. I wanted to see what happens in the limit. Let me remind you. In the limit that theta 1, 2 is 0. So this will be the unity matrix here. And this was what? Cosine theta 1, 3. Sine theta 1, 3, e to the minus I delta. Let's repeat this. Minus sine theta 1, 3, e to the I delta 1. Cosine theta 1, 3. Somewhere. And then remember, as I said there is this phase. But then I argued that I could simply multiply the whole row by e to the I delta and put it here. The thing, and I don't think I answered you. I think I remember that Ahmed was confused. He wanted to understand. When I multiply the row the same way, remember this is the matrix that acts between UCT bar and then DSB here. So this is the third component. This is a phase of the B core. I think I didn't say it right. I said, well, let's do some overall phase. Then I can always rotate the phase of the B core. I can keep rotating. Remember where I put my phase. And this is why, by the way, some people use different form of Kobayashi-Maskawa matrix. For example, Kobayashi-Maskawa used a different form for what is called Kobayashi-Maskawa matrix today, because we don't use Kobayashi-Maskawa matrix, we use Kyung-Chow, which is PDG. It became popular. So, and then remember, by doing that, by redefining this, I put the phase here. Then I said I can multiply this by e to the minus I delta. That's a phase of the top core. I can do that. And this is just to remind you, when you think you have a CP violation, you think you have it. It's not enough that you have the phase. You have to make sure you can redefine it away. But we started by concluding here with theta 1, 3, 0. Then, of course, phase is 0, trivially. It's not there. But also when theta 1, 2 is 0, there is no phase. I can get rid of it by redefining bottom and top phases, okay. So it's not a physical phase. And similarly for theta 2, 3, it will be on the left, same argument. Okay, all I'm proving now is that in these subcases there is no phase. I haven't yet proven that there is a phase. This was just counting. So we are hopeful that a phase actually exists when these angles are non-zero. Okay, but even then we better be careful. Okay, so we'll comment on that. Which means that the epsilon CP must be proportional to sine theta 1, 2, sine theta 1, 3, sine theta 2, 3, sine delta. And not only that it wants to be small, it wants to be too small. Okay, so it's a nice question to come and direct. Why? Because this is about 1/5. This is 4 times 10 to the minus 2. that this is few times, I think, also of the order of 4 times 10 to the minus 3. So notice it's quite small. So there must be some enhancement that we'll talk about. But at least it wants to be naturally small. The beauty of the standard models, you don't have to postulate the smallness of this strange thing. See, once you sort of had your parity violating theory, the values of the physical mixings give you naturally small CP violation. Okay, but let's see then what we have to spend a little time. Let's see really what goes on in this K-meson system, the sort of prototype CP violation, right? It all started in the K-meson. So I'll just do K-mesons. We can do B-mesons like that and other. Remember how we started to be worried? Without the charm quark, I had a problem. So your mind convention is that the quark masses are positive numbers, okay? We like to speak of masses as plus 1 GeV, right? Minus 1 GeV. Just a convention. The mass of the quark. Sign is not meaningful. Remember when there was no charm quark? No charm. Now I stay with 2 generations, okay? I want to simplify my life. I don't want to discuss CP violation. I want to get K long, K short mass difference. So let me start with 2 generations. Without the charm quark, I don't have the right structure. And there was something else. I had this flavor violation, if you remember. I had the interaction cosine theta cavivo, sine theta cavivo, if you remember. S bar, gamma mu, A plus B, gamma 5. You and I know A and B from the homework, Z mu. And that was a disaster, if you remember, because, why? Because when I exchange Z, I get directly a 3-level flavor violation, which was I got something on the order of sine squared theta cavivo, cosine squared theta cavivo, G Fermi. Exchange of Z is G Fermi at low energies. It's like double.
No, third square.
Then we got this S bar gamma mu D squared. And we estimated this. We concluded that this will produce a change in the K-ion KK bar masses. Why? Because this changes strangeness by 2 units, and therefore you can take me from K to K bar. The mass matter is a static Lagrangian, therefore it's a mass, static energy, static Hamiltonian if you wish. Therefore it produces delta mk. Delta mk changes strangeness by 2 units because connect states of K and K bar. And we got the delta mk over mk, I hope you remember, was sine squared theta cavivo, G Fermi, Fk squared. Fk is the K on decay constant, which is roughly of order of GeV. And we estimated this is about 1 over 100, let's say. Actually a little smaller, but okay, to get it as small as possible, 1 over 100 times 10 to the minus 5 in GeV times 10 to the minus 2. So I will get 10 to the minus 9. I'm 5 orders of magnitude off. It's 10 to the minus 14. Fortunately, there is a charm quark, okay, so this is the first beauty of the standard model. Charm quark made sure that I got cosine theta, sine theta, minus sine theta, cosine theta. We have 2 contributions. We got flavor diagonal, only d bar d, and therefore this effect was killed. And this is the thing that you love. Okay, this is a beautiful example of how field theory works nicely when the theory is normalizable. You have a quantity which is 0 at the 3 level. You can sit down, you know, roll up your sleeves and compute all kinds of loop effects. Don't worry about renormalization or anything. This was 0, and what you compute better be finite. And actually, it's probably the best, the prototype, really, the nicest example of the calculability of the spontaneously broken gauge series. And let me illustrate it. And I'd say a few words of what happens in various gauges. Remember I told you can think in unitary gauge, but better compute in R gauge. And maybe to be on the safe side, you rethink how to compute in the unitary gauge. Let's try to sort of see what goes on a little bit. I'll skip the details. I think this will make a great homework or take-home problem to compute. It's much nicer if you guys do it. Put the numbers. And it's discussed in basically all the books, so it's not that hard as it would be. And the book that I mentioned, like Palashpal books or book or Cheng and Lee and so on. I think it's right there. But most of the subtle features are not discussed carefully. Okay, so let me try to hold your attention for a little while today. So if it's 0 at 3 level, I start at 1 loop. So let's look at the loop. Remember, I'm with 2 generations. I'm not looking at CP violation. And at 1 loop, the only diagram that I have, it has to involve a W, but because it's neutral, it must involve 2 W's. It cannot be 1 W, that would change flavor, right? Change charge, sorry. So I must put 2 W's. The rest is easy. So that means that I have a strange quark coming out, D quark entering, strange quark, anti-strange quark in the end, so that I have S bar D, and at the end S bar D. So who can propagate here? S, let's start from here, S charm or up quark. Okay, I got to be careful, so I need you to be awake, okay? Not to screw something up. So what is going on here? Which W is going here? This is positively charged, right? 2/3 minus 1/3 plus 1. It's good. Positively charged minus 1/3. So again, I have U and C. So it's okay. This is the basic diagram I have to compute. So how you would idealize compute it? Well, there is each vertex has G over square root of 2. So I'm going to have G's over square root of 2 to the 4th. I want to compute a static quantity, static Hamiltonian, 0 external momentum. T external. I want to compute the K long, K short, or KK bar, as we say, mass difference. So that simplifies things. So I have D4K over 2 pi to the 4th. Just want to show you that we could do everything with all the coefficients, everything. Then we'll have S bar, gamma mu L. Remember the vertex is S bar, gamma mu L. And what is propagating here is an up quark. Up quark to down quark is cosine theta. I'll get cosine theta, sine theta kabib. Okay, you remember that? Up quark cosine theta, down sine theta charm. Then I have K slash plus M up, K square minus MU square. Correct? But there is also charm quark, as Jorge says. So I better include it. Remember, it has a minus sign. The Cabibbo rotation, well, you know it in your dream, is CS minus S. Cabibbo. Then I have, that's all, and D. I close D here. So I call this vertex mu, and I call this vertex mu. I'm going to call this alpha, and I'm going to call this beta. It's okay? Vertex. So I will have S bar beta, gamma beta L, and the same thing again. These lines are completely identical. Right? I propagate again. So I have the same quantity. But what did I know? I missed something. Gamma nu L. See? I told you you have to check on me today. I really don't feel bad. If I were to sit down, I would just fall asleep, okay? Just when you start talking, you wake up, you can, it doesn't matter how sick you are. We agree? I call gamma beta, the same thing, and then I'll have gamma alpha D. And then I have twice the propagator of the gauge boson. Which gauge should I use? Unitary gauge, I get a lot of divergence, okay? So I'm scared of a unitary gauge. Let's use that, arc psi gauge. Arc psi gauge is a mess with that guy. Let's do psi equal 1. And then let's worry later on what is going on. So I'll take arc psi gauge with psi equal 1, if you don't mind. How does the propagator look like? This I can erase. I need now the blackboard. I better use it intelligently. So d mu nu in the arc psi gauge is minus I. Well, I'm not writing a factor. No, just this. But there is also the unphysical guy. I'll have to think about that, which is I k square minus mw square. This is psi equal 1 gauge. You may say, why not do the unitary gauge? Okay, you'll see later on what's better when I do the unitary gauge. We are all still okay, with hunger and all that. Okay, so what does then it's very easy. Then my propagators have G nu beta, k square minus mw square, E mu alpha, k square minus mw square. This is the complete expression. I have twice. This is called the Jim propagation, okay? This is always emphasized. This essential fact. When I claimed if the masses are degenerate, then there is no mixing. How convincing it was, I don't know, but take the masses to be the same, what do I get? I get 0 immediately. I get the Jim mechanism in its full glory. In order that Cabibbo mixing, or whatever Kobayashi-Maskawa mixing, be physical, masses must be non-degenerate. Particles can't be non-degenerate, and they must be different. Now tell me, which piece will go through, K slash or M? It will be K slash because L goes twice to remain L. If I go through M, K slash becomes R here, and that's a disaster. Okay. So these do not contribute. So I notice immediately two things. First, that the masses must be non-degenerate, and the effect is proportional to masses squared, not linearly. That's how the Jim works. Okay, because the rest is only the square of the mass. So what we get here, so this continues here. This is G squared over 4. Then cosine squared theta cavivo, sine squared theta cavivo. I'll drop. I'm going to drop cosine squared, that's 1 basically. And then what do I get? I have an integration d4k over 2 pi to the 4th. Now, I go through k slash, we said. I will have twice k slash. So let me be clear here. S bar, gamma mu, k alpha, gamma nu LD, S bar, gamma nu, beta is equal to nu. Oh, lower. Gamma beta. Then not k alpha, gamma alpha, S beta, not k alpha, I already have alpha. So gamma, what? Gamma rho. I don't know, gamma rho. Gamma beta, gamma omega. No, gamma nu here, gamma mu. Right? Beta is equal to, are you following me? Beta is equal to nu. And mu is equal to alpha. So it's mu and mu. Beta became nu in this case. I have k rho, k omega. I have k slash twice. Okay, I know I'm maybe boring you. And then I get this quantity in the bracket times S bar gamma mu LD, S bar gamma mu. Why don't I have LD? Why in the world I don't have LD? K rho, K omega. 1 over K squared minus MW squared squared. And then I have this strange thing which goes like this thing. What is this thing? This is K squared minus MC squared minus K squared divided by K squared times K squared minus MC squared. Everything squared. I'm going to take mu equal to 0. It's completely negligible. So K squared cancels. And I will get MC to the 4th over K to the 4th, K squared minus MC squared squared. I have that twice. I have to square it because I have it both in the numerator and the denominator. Okay. So this is when the dust settles.
Sorry, where the gamma rho comes from?
Gamma rho is K slash.
Is K
K slash is gamma rho, K rho. Another K slash, gamma omega, K omega.
It's not cancellable?
No, I go through K slash here. K slash goes out. It's not cancelled, they are different.
Okay.
No. It's
okay,
very different.
okay. You take it out.
They don't cancel it.
Okay.
Right, it goes through K slash. No, it's very important. If the masses were the same, it would cancel and I would get a 0. Correct. I would just get a 0.
Okay.
Oof. No, we have come out. I would have just skipped it, but I want you to appreciate it. First, this integral over k rho k omega in the symmetric integration is just 1/4 k squared. Right? This. Only the diagonal piece contributes, right? And it's 1/4 k squared. This is g rho omega k squared 1/4. So this is g squared over 16 sine squared theta k viva. d4k I can write as k squared dk squared. There is pi squared. So now I'm going to get here over pi squared with some factors. So let me write proportional now. I'm not going to compute. Notice what I get. I get S bar gamma mu, gamma alpha, gamma nu, LD. S bar, gamma nu, gamma alpha, gamma nu, gamma alpha, gamma mu, LD. And then I get k squared, I had here, over k to the fourth, k squared minus mc squared squared. And there was a factor here, I'll take it out, mc to the fourth. G to the fourth over 16, well 16 now, I'm not caring about factors so much anymore. mc to the fourth sine squared theta k viva. And I missed something, which is k squared minus mw squared, everything squared. Notice that I have k squared, k to the fourth cancel. So I have dk squared, and this is k to the fourth, k squared, k to the sixth. I don't like that. No, to the did I do this right? I had k slash, which was k squared. mc to the fourth, so probably it's correct. I have mc to the fourth. Let's see the dimensions. mc to the fourth, so this is the... Remember, this effective Lagrangian is a 4-fermion Lagrangian. It's dimension 6. We got the strength at 3 level, which was G Fermi. It has to be G Fermi, right? This guy's a dimension 6. You agree? There are 4 fermionic fields. So it must be 1 over m squared. I get m to the fourth, m to the 6, but I get 4 and 4, 8. It's good. Dimensions are good. Now, just a few comments before I let you go. We need, unfortunately, a little more time. Well, we started late. It seems that it goes as mc to the fourth. I mean, the first time when I looked at it, I even made a bet that this is going to go as mc to the fourth, and I lost the bet. Okay, it's very tricky because you know, you don't want to look into a book, but you want to get a feeling. Okay, you say, but look, it goes as mc to the fourth. How can it not go as mc to the fourth? And I want to show you this important subtlety. This diagram is completely ultraviolet convergent. It has huge powers of k squared, and it has to be. There was no counter term at the 3 level, and this is now the proof of the realizability of the standard model. I'm getting a finite result. But the more powers of k squared accumulate below, the more danger becomes in the infrared. Obviously. So the ultraviolet infrared, there is an interesting thing, you know, when it's ultraviolet bad, it's infrared good. When it's ultraviolet good, it may be infrared bad, and lo and behold, look at it, let's put MC equal to 0. Just to see what happens, okay? No, of course, outside is not 0. Now I'm just looking at this diagram, sorry.
Higher.
If I put MC equal to 0 here, I get a bad infrared divergence, which is quadratic. I get dk squared over k to the 4th. That's dx over x squared, it's quadratic. This loop, and I'm not going to compute it, but you will compute it, okay? There are no external momenta. This is proportional as 1 over MC squared. MC squared. So it happens. So I'm going to make a long story short now. I'm going to summarize. I wanted to see that you are able to do the calculation. I'm going to take 1g squared into the definition of G Fermi. I'm going to get G Fermi here, sine squared theta cabivo. This is what I had at the 3 level that fortunately went away. It was G Fermi sine squared theta cabivo. Then I will get another G squared, 16 pi, something like that. I get alpha over 4 pi. That's actually what you get. And you're more careful with the coefficients. Okay, just because there is G to the 4th, you're with me.
Yeah.
Then I will get M charm squared. And the dimension tells me it must be over MW squared. The dimension is here. There are various ways you can do this, taking dimension. And the diagram is completely finite, okay, ultraviolet. This is what you get. And then you get this thing. Now this is called, there is something which is called fiercing. This is not trivial, but a number of books do that. Chengel Lee does it, for example, the S bar, gamma mu, gamma alpha, gamma nu, LD, times S bar, gamma nu, gamma alpha, gamma mu, LD. Is actually, I don't remember the number. It's S bar gamma mu LD. S bar gamma mu LD. Maybe it's better if I make it lower somewhere. It turns out that it simplifies with just 1 gamma mu. There are these things, you know, with Pauli matrices you get relations like that, but also with gamma matrices, okay. Maybe you have some experience. Notice the difference between what we had in the 3-level case, okay? And that is to say, we get a further suppression, which we could have guessed. The only thing I took some time to show you that it has to be quadratic, dependence on the charm quark mass. Actually, there would be a difference. There would be m charm square minus m up square. I ignored m up. And it's not quartic because of the infrared divergence. It's quadratic. This is very important. You will see how crucial and important it is. That the leading contribution is for a number of reasons. So in other words, there is a further suppression. So in other words, when I compute delta mk over mk, it's not G Fermi sine squared theta cabivo fk squared, as it would have been at the 3 level. If you have 3-level flare violation, it becomes dangerously fast. 3-level, it's a order G Fermi, Cabibo suppression. Fk squared is just the matrix element sandwiched between k and k bar. There is a further, it's called the Jim suppression, alpha over 4 pi, which is a number of order 10 to the minus 3. 10, a number of order 1 over 100. And another contribution, which is m char over mw squared. This is another number of 10 to the minus 3, actually a little smaller. This may be a little bigger, but this is a little smaller. M char is about 1.5 GeV. And mmw is 80 GeV. By the way, in their original paper, so notice that this was roughly, I estimated to be about 10 to the minus 9. I get 10 to the minus 15. The number is few times 10 to the minus 15, 10 to the minus 14. Without putting the numbers, I get, this is a celebrated success of Jim paper, okay? That mind-boggling is these people never got a Nobel Prize, okay? Not only predicted a new particle, okay? They predicted the physics associated with the particle, they predicted the mass. They said it should be lighter than a few GeV. They estimated it. Then a few years later, it's very interesting, in 1974, Gaillard, Mary K. Gaillard, one of the few women in our field at that era, with Benjamin Lee and Gaillard, computed this precisely. And they actually predicted the charm quark mass to be 1.5 GeV. And more or less at the same time, experiment found the bound state of charm quarks, okay, celebrated JSI experiment at Brookhaven and Slack, and confirmed this beautifully. We are almost there. So you see, because people are sometimes confused here, and they thought of there is something which is called the flavor problem. People often worry, how come there is no more violation of flavor? And they say, well, the answer is Jim. I want you to appreciate it's not automatic. People worry about that when they worry about new physics, what could be beyond the standard model, maybe at LHC. And the point is, you see how the standard model lives dangerously, okay? It works only because charm is light. If charm weighted 10 GeV, this would completely fail. So it's not just the structure of having the charm to this cancellation and so on. It's actually the value of the parameter, okay? So there is nothing magical about these values of the parameters I want to argue. They are what they are. And now let me comment how even more dangerously it works, because you will tell me, well, but what about the top quark? You pretended there was no top quark. That should contribute much more. Because if M charm goes as M charm square, and top square should appear as M top square, that's how many? 10,000 times bigger, right? Charm is 1.5, top is 175, so 110,000 times more. So why is it that charm wins?
Because the
angles are small. Many years ago, I remember 1981, with my collaborator Marciano, we were studying supersymmetric unification. And it didn't seem to work, and we fell in love with supersymmetry, and we argued that everything could work, 1981, if top quark were to weigh around 200 GeV. Many people told us we were crazy. We said, no, this is terrible, because then theta 1,3 would have to be terribly small, and that's very ugly. Cannot be like that, okay? There was a prejudice in 1980, in 1981. People would tell you, oh, top quark should weigh less than 20 GeV, because it cannot be that it's so ugly. But this is the way it is, you know. It may not be nice, because what we said, this is small, the top quark contribution, why? The top quark will go with theta 1,3, coupling to down quark, theta 3. That's already very small, even without squaring. Remember, this is order 10 to the minus 2 times 10 to the minus 3, a bit more. Just by itself it's small, okay. So actually charm dominates. When you compute KK bar, this is the contribution. Now, if I want to compute CP violation, then of course it cannot be, because there is no phase. So if I do the CP violation, okay, just a few words more, I have to include the, oh, an important comment before I do that, I'm sorry. I forgot completely, and then you forgot to ask me. That in this case, there is also G propagate. With the same mass in the propagator. So I should include this diagram. So instead of W, there will be G plus. Where does it come from? It will come from the Yukawa. In other words, you and I will derive the doublet. In this gauge, the leading term will be G1 plus IG2, V plus H plus, well, I don't know what it is. I don't need this. I just need this guy. And this I would call G plus times square root of 2, V plus H, 1 over square root of 2. There is another degree of freedom, which is the unphysical Higgs of the Z boson. The Z boson is, I don't care about the Z boson, just the W. So there will be this guy. And it's very easy to see. We'll come back to it because we have to study a bit. In various homework examples, I ask you what happens when the gauge coupling goes to 0. Okay? And there was already top pole decay, and the amplitude didn't vanish. And I think some of you, I think it was Julian, even knew that there would be unphysical Higgs. I think it was you. Anyway, I had a quick look. Notice that I would have 4 times Yukawa charm coupling. Right? Because the charm quark is proportional to Yukawa charm, and Yukawa is fermion. Remember what we got?
Mass of fermion over mass of the
W. So in other words, this diagram is proportional to MC to the 4th. It is truly proportional because there is no more gym inside. There is no more cancellations, okay? This we could easily check. This had to go as, no, why don't I leave this? Sorry. If I do everything, it won't be so useful. The thing is, you will see, I don't propagate up quark anymore. See what happened in the W case, I propagated charm and up, which came with a minus sign. So the diagram became more and more ultraviolet finite. 1 over k square minus 1 over k square. Here you just propagate charm. You can take Yukawa up, which is m up over mw, roughly proportional. You can take it to be 0. So there is no more chimp, it's already here. And this is small. In other words, in C equal 1 gauge, the W contribution proportional to MC over mw squared, and the G contribution MC over mw to the 4th. I think we can come back to the unitary gauge. I think it will be a bit tiring if I talk about it. This should be correct in the unitary gauge too. Or maybe you can, let's see if you can guess from what I said. Okay, just a few more minutes. So I conclude in the arc psi gauge that I worry only about W, because the unphysical Higgs contribution is small. You got this? Please ask me any question. Now. Okay. Then you can ask, suppose you go to the unitary gauge. If this is true, in the unitary gauge, what is the propagator? Is G mu nu minus K nu over mw squared over K squared minus mw squared.
Unitary means 0 equals to 0.
Sorry?
The, how is it called? The side, the thing, I think, equal to 0.
No.
No.
No, it's strange, okay? Let me remind you. The chart. If someone remembers what is the unitary gauge, it's important.
Okay.
Well, think about that. No. What is the in psi gauge? What is the propagator of G?
Sine. Sine.
So what will be unitary gauge?
No, 0. No. Infinite.
Because if I put chi equal to 0, this guy propagates and he has a 0 mass, okay? He behaves like a Goldstone boson. So which psi corresponds to unitary gauge?
Infinity.
Infinity. Which you should do after the calculation, okay, to be on the safe side because of the divergences. But this is one example that you can work with the unitary gauge. You know why? Because I computed with this, right? But you tell me, okay, but now you should include this in the unitary gauge. Remember what I had? I had m charm to the fourth when I worked with this, remember? Then times my integral. If I include this, what happens is in the unitary, in the symmetric integration, I'll get an extra k squared, at least. So what happens is, I make it worse ultraviolet. It will diverge. Actually, the worst term will go as k squared over mw squared. But it will help in the infrared. It's order mc to the fourth. It's negligible. There was mc to the fourth. In the first piece propagator, we had k squared, dk squared, then we had k squared, then I will remind you k to the fourth, k squared minus mc squared squared, k squared minus mw squared. This cancelled. The problem was when charm mass goes to 0, I get an infrared divergence. But if I put extra k squares here, I kill the divergence at first logarithmic. So this is actually proportional to mc to the fourth, in which case I have to introduce I have to redo the calculation. This is not what I'm computing, okay. I have to then separate that, and that will come out of here. So this is not to tell you that I would advise you to use unitary gauge. It's good to, if it can be seen what happens, do it, just to see once again, to convince yourself that it works. But the safe thing is, either psi equal 1 or generic arc psi. So if you wish, if you and I had worked in the arc psi gauge, there would be a piece here which depended on psi, remember a function of psi? There would be g which depends on psi, and they would be proportional to mc to the fourth, and they would cancel each other at the end. There are no divergences, okay, people sit down and do that. But you and I, that we want the leading piece, which is mc squared, we don't have to worry about that. Okay, that's the physics of, and I ask you just to think a little bit when I do the CP violation. If I want to do the CP violation, then I must propagate the top quark. If I don't propagate top quark, there will be no CP violation. Of course, you're saying, by the way you wrote the thing, there are phases. Well, you will see that the phases appear. You have to include all that. So that means that you will get here theta. So this is strange, this is down. So this is theta 1, 3, theta 2, 3. For small mixings, sine is equal to the mixing. Then what do you think I should put here, top or charm? Which will be dominant? Charm. I just need one top. Okay, I just wanted to appreciate it. This turns to dominate. It's true that the mass of the charm is small, but who cares? Here there is 1. No, here there is theta Kabiba. Here there is basically 1. Or vice versa. Sorry, this was strange. This was down. So this is 1 and this is theta Kabiba. So this is the contribution. So notice that we have here theta 1, 2. Remember I argued there will be always, no matter what you do, there will be theta 1, 3, theta 2, 3, theta 1, 2, otherwise there is no phase. and one of these vertices here, there was a phase, if you remember, e to the I delta. So there is a phase, and we will get the epsilon Cp is of order theta 1, 2, theta 1, 3 for small mixing angles times delta. But there will be also a term which is m top over m charm squared. So I'll get enough enhancements to save me, or linear. I'm sorry, I don't want. It's late and we're tired. And it will work out. It's a non-trivial calculation. You have to do all the factors correctly. Okay, it will work out. It won't be too small because there'll be enhancement. You know, after all, what is CP violation? That's imaginary versus real part in the KK bar, right? Remember that from Alexei. I wrote it MK, and I wrote as if this is real. No, this is a real part of delta M. There is a real part of delta M. There is also imaginary part. And so the CP violation is the relative value of the real and the imaginary part. And the real part goes with M charm, the imaginary with M top, so it saves you from being too small. Standard model works, and this is really remarkable, with this one phase. Not only that it fits nicely, this explains all the CP violation. And all other CP violating effects, which is not just KK bar missing, direct decays, ion decays into 2 pi and so on. Okay, that's a subject in itself, but it's very technical, very lengthy, and we will skip it. We have still a lot of basic physics to discuss, especially decays. Okay, this may have been today a bit.
Is the tutorial still happening on Friday?
Oh, the tutorial is supposed to be on Friday?
Yes. Well, it was scheduled.
It was scheduled for Friday, what time?
4. Like
4.
But if we haven't done
Let me talk to Andrea. I don't know if he can manage to do it for Friday.
Should we send the next one?
Yeah, well, I will include a message now on the official. And I send you a message with saying to Andrea and introducing Andrea to you guys. And let me talk to him. Well, if you would do, what did you discuss? Well, I know you. That's it?
Yes.
We go and eat?
Yes.
Yes.
Good.